Gonna record this. So welcome everyone. We are now on our week 3 of Statistics 101 for your PhD program. And the topic for this week is epidemiological statistics and the measures of diseases, occurrence, and risks. So the typical measures that we do in epidemiological investigations are proportions, ratios, and rates. These are the common data that we deal with, and typically they will indicate whether an individual was exposed to an illness, has an illness, experienced the injury, became disabled, or dead. So the outcome typically in epidemiological study is, illness, injury, disability, or death. And it's always about exposure and non-exposure, and then the outcomes. So that's what epidemiological investigation is all about. And then we describe those epidemiological data with the use of ratios, proportions, and rates in order to really present the data to the public in an understandable manner. At the end of the day, epidemiology concerns a huge number of people, typically, a whole barrio, a whole city, or a whole country. And so we definitely need to use common terminology that can be easily understood by the public. So as scientists, as epidemiologists, we all need to be mindful that the ultimate consumer of our report is the public. And so we have to make it easy and understandable to them. So back to the basics, just the definition. What is proportion? It is the fraction of a total group associated with disease or other factors. In proportion, the numerator is always part of the denominator, and it is commonly expressed as a percentage. So let's do a quick example. Put your answers on the chat. 100 students currently smoke cigarettes among 300 total newly admitted students in the School of Nursing at CDU. So what is the proportion of smokers among newly admitted students? So based on the formula of proportion, it's the numerator is always part of the denominator, and then it's commonly expressed as a percentage. So when it expresses a percentage, then there might be some multiplication that needs to be done. So where are your answers on the chat? Let's see, here's our chat. Okay, very good. So, the answer is 33%, because basically there are 100 students who currently smoke, and we divide 100 with the 300 because that's the total of the students. So again, it's the fraction means the 100 students of a total group means the total is 300. So 100 divided by 300 is equal to, basically, if you get your calculator, that will give you 100 divided by 300 equals 0.333. 3. But then, because it is expressed in percentage, you multiply that by 100, and that gives you 33.33%. So I think everybody got that. So we'll proceed to the next slide. So calculating a proportion, another example here. So get your pen and your calculator. Calculate the proportion of men in this study who were diabetics. We have the numerator, 189 diabetic men, and the denominator is the total number of men. That's 3,340 or 3,340. So what is the proportion of diabetic men? Let's take a look at your chat answers. So again, I have my calculator and I would just put, so correct answer is 5.65. Very good. Somebody got the correct answer. And yes, I'm sorry I forgot to let you get a calculator. There's always a calculator, by the way, on your laptop. But that's hard to find when you're also watching the video. So I always have my calculator on the side. So, all right, well, we get the correct answer by dividing the number of diabetic with the total number of men, and then we multiply it by 100, and the correct answer is 5.66%. All right, so another example here is the calculate the proportion of deaths among men. So here the given is that the numerator are the deaths in men, and there were 100 deaths in diabetic men plus 811 deaths in non-diabetic men. So the total number of deaths in men is 911. For the denominator, there were, which is the total or all of the deaths. For the denominator, the reported deaths in men is 911, and then there were 72 deaths in diabetic women and 511 deaths in non-diabetic women. When you add all of that deaths, you have a total of 1,494 deaths. So what is the proportion of deaths among men? So let's get our calculator. So the deaths in men, the total is 911. We divided that with the total, because the 911 is just a fraction. And so 911 divided by 1,494. And then you multiply that by 100. And that should give us, let's see what your answers are. Very good, 60.97%. So don't forget to put the percent, because proportion is expressed in percent. That's why we multiply it by 100. So always remember, by the time it's exam time, I will be looking for the percentage, because that tells me that you totally understood the concept that proportion is expressed in percentage. Next slide. Ratio. So in contrast to proportion, a ratio is one number divided by another, like in proportion. But the numerator this time does not have to be part of the denominator. So that's the main difference between proportion and ratio. So for example, 100 students smoke, 200 students do not smoke. So the ratio of smokers to non-smoker is 100 over to 100, or 1:2, or 0.5. And then in simple terms, for every student who smokes, 2 students do not. Always remember that when we report ratio, we must use the lowest common denominator for the numerator and the lowest common denominator for the numerator and also the lowest common numerator. Lowest common numerator and lowest common denominator. So that's why our 100 over 200, we use 1:2, because 100 is our numerator and denominator, our common denominator. So 100 divided by 100 is 1, 200 divided by 100 is 2. And that's the lowest level that we can get in expressing our ratio. And then we can also simply put it as 0.5, because 1 divided by 2 is 0.5, which is basically half. But that's not the way. The real reporting for ratio is really 1:2. We don't report, the ratio of smoker to non-smoker is 0.5. That's not a typical way of reporting, but people will understand that. However, it's better to report 1:2, because that's the typical reporting of ratio in common public language. So calculating a ratio, I'd like you to try this. From a cross-sectional study exploring the breast cancer risk factors in Utah, 704 women indicate that they had 1 or more children, and 132 said that they never had a child, with 12 not responding to this question. So what is the ratio of pairs to non-pairs women in this study? So we'll go to your chat section. So basically, the definition for pairs are those with children, and non-pairs are those women with no children. So based on the given, we could simply just put 704 divided by 132, right? So 704 divided by 132 equals 5.33. So how do we interpret the 5.33? Because it's a high number. Then it's more than 1. It's more than 1:1 ratio. So every time it's more than 1:1 ratio, the word that we need to use is 5.33 times higher. So you always remember that the right word to follow would be higher. So it would be 5.3 times higher, or 5.3 times more women with children compared to women with no children. So that's the way how we report the ratio in this study. That the women with children is 5.3 times higher, or 5.3 times more than the women who had no children. Another example for ratio, I'd like you to get your calculator, is on infant mortality rate. So Delaware is one of the states, one of the 50 states. So Delaware's infant mortality rate in 2001 was 10.7 per 1,000 live births. That's a typo there, sorry. And New Hampshire's infant mortality rate in 2001 was 3.8 per 1,000 live birth also. So calculate the ratio of the infant mortality rate in Delaware to that in New Hampshire. So what would be your answer to that? So basically what we need to do is, oh, hold on. We are now in Delaware. So we need to simply divide 10.7 divided by, because it's Delaware to New Hampshire. So what is the rate in Delaware? Was 10.7 divided by the 3.8 infant mortality rate in New Hampshire equals 2.81. So what we're going to report, because again, it's more than one, a ratio of 1:1 is equal, but every time we get more than one, then we simply state that Delaware has 2.81 more, or 2.81 higher in infant mortality rate when compared to the infant mortality rate in New Hampshire in 2001. So that's the way how we report this statistics. And let's see if we have the correct answers from the chat. How many of you said 2.81 higher? Very good. All right, I see. All right, I see the word to use the word higher, and that's really a very correct answer. The word higher has to be there, or more times, or because anything that's higher than 1:1 ratio, it needs to be expressed as higher or more often or more frequent. Okay, and the next one here, rates. So rates is very easy. It's defined as a measure of the frequency with which the event occurs in a defined population over a specified period of time. So it's self-explanatory based on the definition. And what we typically use rates in reporting epidemiological statistics is when we're trying to compare disease frequency in different locations at different times or among different groups of persons. And the example there that I put in is, what is the anaphylactic reaction rate when there are 2 anaphylactic reactions reported per 100 patients who receive rituximab, which is a monoclonal antibody that's still murine. Murine means it has a component from rat. So you could just imagine it's not fully humanized. So we expect that there will be a reaction because the medication is not fully humanized monoclonal antibody. It's made out of antibodies from rat, if it's from the murine model. So there are, in this example, there are 2 anaphylactic reactions reported per 100 patients who receive rituximab, which is a murine monoclonal antibody, as a first-line therapy for follicular lymphoma, because rituximab is an anti-CD20 antibody, and lymphoma are B cells disorder, and B cells are almost CD20 positive. So if you want to treat lymphoma, you want to give an anti-CD20 medications or anti-CD20 monoclonal antibody, and that's what rituximab is all about. So rates is just simply how many, what is the frequency? So here, it's just basically 2 per 100 patients treated. So that's the answer to what is the rate of the anaphylactic reaction for patients who receive rituximab as a first-line therapy for follicular lymphoma. And the answer is 2 per 100 patients treated, because the definition is defined as a measure of the frequency with which an event occurs in a defined population. So the defined population here are the follicular lymphoma patients, first-line therapy over a specified period of time. So that is what rates is all about. The second example there is patient death rate is the number of deaths after 60 days of open heart surgery at St. Luke's Hospital. So we know that open heart surgeries are very complicated procedures, and one of the benchmark of the success of an open heart surgical program is usually survival after 60 days. So most of the hospital accreditors or surgical program accrediting body would always want this type of statistics, patient death rate, very specific after 60 days of open heart surgery. So it's a measure of the frequency with which the event occurs in a defined population. So the population here is open heart surgery patient over a specified period of time that is 60 days after they had the open heart surgery. And what is that number? What is that frequency? So if St. Luke's has 60 deaths after 60 days of open heart surgery, that can be benchmarked with, if PGH, Philippine General Hospital, only has reported 48 patient death 60 days after their open heart surgery, then one could really start investigating as an epidemiologist what is the reason why St. Luke is having a higher patient death rate compared to Philippine General Hospital. So I hope you appreciate, when do we use this kind of epidemiological statistics? Well, basically we use this when there are stark differences in the rates, particularly in outcomes of diseases based on treatments or outcome of diseases based on surgical interventions. So rates are very important. And then percentages and percentage change. Now, percentages simply means that it's per 100, and that's why we multiply the number with 100. While a fraction is something out of 100, just like what we discussed in the earlier slides. Now, percentages could be not so meaningful, but when we use the percentage change instead of just percentages, that could be of interest among scientists and epidemiologists. For example, using the formula for percentage change, which is dividing the difference between the two numbers by the starting number. So this can be tricky. Divide the difference between the two numbers by the starting number. So here's the problem. What is the percentage change when Pfizer reported an increase in annual sales of Lipitor from 50 million to 75 million. So let's grab our calculator. Divide the difference between the two numbers. So what's the difference between the two numbers? 50 to 75, what is the difference?
Billion.
That's 20, 25. And so, and then you divided that by the starting number. So 25 divided by 50. That is
0.5.
0.5. Okay. And what does that mean? You still have to multiply that by 100 because we're talking about percentage, right? So that means that there is a 50%. 50% increase. So it has to be reported as 50%. So let's take a look at your answers in the chat. Did you answer 50%? Percentage change. The one that says 0.5 needs to continue to multiply it by 100 because this is percentage change. Every time there's a word percentage, it has to be always multiplied by 100. All right, and then let's do the second example here or problem. What is the percentage change when the Department of Transportation reported, another typo here, a decrease in annual number of fatal car crash in New York from 75 to 50? So follow the rule of divide the difference between the two numbers. The difference between 75 and 50 is 25. But this time, it will be 25 divided by 75 because the first number is 75. So what would that be? 25 divided by 75 equals 0.333. But you have to multiply that by 100 because it's a percentage change. And that will give you, let's see what everybody says. Very good. A 30% percentage change, which is really, really quite high. So by the time we use percentage change, it becomes more meaningful to the reader. It becomes more usable information. Because if you just say 50 million to 75 million, what does that mean? We would say, okay, there's a 25 million increase, but actually that's not a 25 million increase in sales. It was actually a 50% change of the annual sales. So it's important to not just look at the number, but to really calculate the percentage change, because by just looking at the number, it could be misleading and it could be misinterpreted. So that's the message, the take-home message of percentage, and making sure that we look at the percentage change rather than the percentages, because it can be misleading sometimes. I can mute some of you so that we don't hear the music. All right.
I have a question.
Oh, yes, go ahead.
For the, when you subtract, do we always use the, or we always subtract the smaller number from the higher number all the time?
It's
Is
not,
it correct?
no, it's we subtract with the first number.
For example, like when we said for the first example, you said 50 million to 75. So we subtracted 75 minus 50, that's 25.
Mm-hmm.
The second example, that's 75 first and then 50 next. So 75 minus 50 is still 25. So it all goes for all, for example, problems that we subtract the smaller number from the higher number. Is it correct though?
It's correct, but
Start.
you have to remember that you would subtract the uh, the difference between the two numbers. We always start. You see here, it's increase, right? Because it's 50
Yes,
million to 75 million. But you see, when you do 75 minus 50, that's a negative, right?
okay, yes,
So
yes.
minus 25, and then you divide it by 75 and you got 33.3. That's why you say 33%
Percent.
decrease, because you have a negative sign.
Ah, okay.
Yeah, you have to be careful because
Yes,
the first one is positive, and so it's increase. Well, this
yes,
one, 75 minus 50 is a negative. It
negative.
went down. So,
Yes.
and
So
that's
that would
why,
help us analyze if it increased or decreased based on the arrangement of it in the situation.
correct, correct.
Okay.
So the percentage change always carries whether is it a increase percentage change or a decrease percentage change, and you have to say those in your answers.
Okay. Thank you, Doc.
33% decrease, because if you say 33% increase, then the answer is wrong, because we
Okay.
actually had a decrease here in the
Yes.
fatal car crash, because it
Fatal.
went down from 75 to 50.
50.
All right,
Okay. Thank you.
very good question. Very good clarification. So here we're going to continue again with percentage increase. 43 graduate students were enrolled in one section of 481, or nursing 481, that's the statistics, in fall 2009. Enrollment in the section decreased by 13 students in fall 2010. What is the percentage decrease? So the 43 and the 43 minus 13 becomes only 30. So 43 minus 30 is 13, right? So 13 divided by 43 equals 0.3023 times 100 equals 30.23% decrease. Did everybody get that? Let's take a look at your chat answer. Yeah, 30% decrease is correct. Wonderful. Again, practice the word adding decrease or increase, because for percentage change, I need to see those words all the time. And then next slide. So analysis of 2x2 tables, which is basically measurement of risk. This is all about odds ratio and relative risk. Both the odds ratio and the relative risk, they compare the likelihood of an event between two groups. There's a subtle difference between the two. It's a very specific rule on when to use odds ratio and relative risk. So let's decipher this. when do we use the word odds ratio, or when do we use this epidemiological stat versus the relative risk statistics? Well, these two are commonly used measures of the relative probabilities of disease in case control studies and cohort studies. Those studies are designed to determine whether there is association. And when we look at association, it means correlation between exposure and development of disease. So expose, disease. And that's basically the premise of the use of odds ratio and relative risk. Now, here's a cohort study. In a cohort study, we clearly identify the groups. Persons are chosen specifically because they were and were not exposed to one or more risk factors. Once they are selected, the persons are followed over time. This can be prospective or retrospective, but the gold standard, of course, is prospective. But retrospective always gives us a very rich preliminary data that we can use as we design the prospective study. So never underestimate your retrospective study design, because it has its own strength. Number one, you don't have to spend money. You just have to dig the chart, right? Whereas prospective, that's when you have to cough up a lot of money and manpower to follow these cases. And sometimes if you do prospective study without a retrospective study, you might really end up not hitting the right note because you have no prior information. So, but again, the gold standard is always prospective. But I don't want you to poo-poo the retrospective study as well, because it definitely has its own value. So in this figure, we have this question: did exposure to tobacco occur before the occurrence of COPD? So we have a population of interest, and then we group them into two. So that's cohort, two cohort. The one who's exposed to tobacco, and the right side is the one, the cohort that's not exposed. And then in the exposed cohort, we look at those who develop the disease, such as COPD, and those that do not develop the COPD. And then on this other cohort, the same thing. The other cohort that was not exposed to tobacco, we also look at the same outcome. Did they develop COPD or not? And that's, this is the standard study design of a cohort study. Now, for case control, it's different. It looks very different. In case control studies, groups are defined as having the disease or not having the disease. You see, in the cohort, there was exposure first, and then determination whether the disease or the disease occurred or not. Here, in case control, there is already disease. They already define those groups having the disease. That's why we call it the case. And then the other group is considered as not having the disease, and this is what we call the controls. So case and control groups are compared as to frequency of past exposure to possible risk factors. And this is a very good design whenever an epidemiologist wanted to understand the occurrences of rare diseases. You see, for rare diseases, how are you going to do prospective studies? Very difficult, right? So we really have to do a case control study in case of following or documenting rare diseases. This is sort of, the case control study is sort of similar to the cross-sectional study. It's just one section, one period of time where the researchers learn about the current disease state and any factors that may have existed. And so here on the left side, you have, these are the patients who had the disease, and we call them the cases. And then based on our defined factors, we determine whether they have been exposed or not with those factors. And then on the right side is our control, are those patients with no disease. And we determine that they have been exposed to the factors or not as well. And that's what we call the case control studies. And this is very, very useful for rare diseases. So going back to when do we use odd ratio and when do we use relative risk? So an odds of an event is the ratio of the probability that the event will occur when the event will not occur. So it's the probability that the event will occur when the probability that the event will not occur. So it's sort of like, this is a very tricky statement. You have to really pause. In simple terms, the odds of an event can be calculated as the number of events divided by the number of non-events. So here in the example, in 100 babies, the probability of a delivery being a boy is 51%. And the probability of being a girl is 49%. So there's a finite number there. 51 and 49 will lead to 100%. So the odds of delivery being a boy is 51 divided by 49, or 1.04. So the odds basically here is that because it's a ratio, a 1:1 ratio means equal. An odd ratio, it's still the same. If you have an odd ratio of 1, it still means the same. So in this case, an odds ratio of 1.04 is really, really low because it's just 0.04 above 1, right? So that's basically what odd ratio is all about. It's the odds of an event that can be calculated as the number of events divided by the number of non-events. So you have, the event would be being a boy, and the non-event would be being a girl, and then you will have the odds ratio. Odds ratio will tell us how much higher the odds of exposure is among cases of a disease compared with controls. Again, the word much higher is there because it's a ratio, and a 1:1 ratio means it's equal. So odds ratio is meaningful when it is higher to 1. And it gives us the idea of the gravity of the exposure based on the value of the odds ratio. If the odds ratio is 10, then you know that's really, really heavy, because from 1, which is 1:1 is the normal ratio, you have 10 times more. So, for example, the odds of exposure or the odds of developing disease is 10 times more for those who have been exposed, then that's really very high, because that's, compared to the normal odds ratio of 1. So compare the odds of exposure to the factor of interest among cases to the odds of exposure to the factor among control. So basically, as I mentioned earlier, when your odds ratio is 1, that simply means nothing. It's just basically that means that the odds of exposure among cases is the same as the odds of exposure among controls. And the exposure is not associated with the disease. 1:1, perfect. So an odds ratio of 1, nothing. The exposure has no effect whatsoever in disease occurrence. Now, when the odds ratio is greater than 1, it means that the odds of exposures, the odds of exposure among cases is greater than the odds of exposure among controls. So those who were not exposed. And the exposure may be a risk factor for the disease, for the development of the disease. So that's why as the odds ratio increases, then we determine that the exposure is a risk factor then. Now, when the odds ratio is less than 1, it actually means that the odds of exposure among cases is lower than the odds of exposure among controls. And therefore, the exposure, instead of being a risk towards the development of the disease, the exposure is actually protective against the development of the disease. So always think that just because the odds ratio is less than 1 doesn't mean that you can ignore that. There is a positive when the odds ratio is less than 1, because it could possibly mean that the exposure has some protective effect against the disease. So this could happen because, especially in immunity, for example, for hepatitis A, when you actually are exposed to hepatitis A, we don't even know that we are exposed to it. But then we develop immunity to hepatitis A, and we don't get sick from hepatitis A after an acute episode of hepatitis A, because the exposure is actually protective against the disease. So in the reporting for hepatitis A, you will likely see that the odds ratio is less than 1, because that's an example where the exposure lower the odds and have a protective effect against the disease. Now, in the case of HIV, back in the early 80s, during the epidemic of HIV infection, the odds ratio was definitely very high. So they have defined that you know, exposure to gay men with specific X, so they have defined those traits, had led to the development of the disease. And they reported odds ratio that were really, really very high. So they would say that gay men had an odds ratio of 20 compared to non-gay men in developing HIV, because at that time they looked at the case and control records of HIV cases, and what they found was that the majority were gay men. But now we know that it's not just a disease of the gay men, that it's now a disease without any boundaries when it comes to gender. So here is the way how we look at an odds ratio table. It's really a 2x2 table. In your left column, you will see the exposed, and those, the first row is the exposed, the second row is the non-exposed. And then in the column, you label your cases, so that's those that develop the disease. And you label your exposed as A for those exposed and had the disease, so those are A. And the one that's exposed but without the disease are labeled as B. And then on the second row, the non-exposed but with the disease. So they were not exposed to what we know as the risk factors. So there is this defined risk factors that the scientists or the investigators have predefined. So they were non-exposed, but then they had the disease, so they are considered as C. And they're assigned as the letter C. And for the non-exposed and did not have the disease, this is what we call the control, and they were assigned letter D. So with this 2x2 table, there is a finite number. This is what we call marginal proportion, and you can't go beyond the total of the column once the total of the rows are already determined. You can't change that, right? Because 2x2 table is an exact, it has an exact total. So if you go, what is the total of cases? What is the total of A and C? Once that's already determined, and once you also have the total of the B and D, then everything in your column and all the totals of your column will always be determined by the total of your rows, or vice versa. So the odds of exposure then for cases is the number of cases with the exposure, that's A, divided by the number of cases without the exposure, so that's C. So that's A divided by C. So that's your odds of exposure for cases. Now for odds of exposure for control, it's simply the number of controls with the exposure, so that's B, and then divided by the number of controls without the exposure, that's D. So that's very easy. B divided by D is the odds of exposure for control, whereas the odds of exposure for cases or disease is A divided by C. So how do we get the ratio? Simple. You divide the odds of exposure, which is A times D, And then the odds of exposure from the control, which is BC, and you get your odds ratio. Let's put this into numbers, actual numbers. So here's an example. An outbreak of cyclosporiasis was detected among residents of New Jersey. In a case control study, investigators found that 21 of the 30 case patients and 4 of the 60 control has eaten raspberries. Inserting these numbers into the 2x2 table, so those who ate the raspberries, the yes and the no, and then the case would be those who had the disease. So A, there were 21, and those who did not have the disease and did not eat the raspberry, 9. So for the control, there were 60. And out of the 60 control, 4 only had eaten the raspberry. So you have 4, and that's represented by B. And then for the one that did not eat and did not have the disease, they have 56, and that's represented by the letter D. So as what I've said earlier, once you have a predetermined number of your row, the column cannot be more than the total of the row. So when you have 21 plus 4, that's 25. And when you have 9 plus 56, that's 65. Then the total here is 90. 25 plus 65 is 90. Now, by the time you do look at your total for case and total for control, that is 30 and 60. And therefore, it has a total of 90. So both column and both rows have exact the same total. And that is why this is so important in epidemiological study, because of the exact limitation that you cannot change the number. There's a finite number once you already have determined the cases in your rows, and therefore the cases in your column will always be exactly the same total as your rows. So when we substitute the number, the odds of exposure for cases, so simply put A right here divided by the C, so that's 21 divided by 9 is 2.3. The odds of exposure for the control, which is your B divided by D, that's 4 divided by 56, and that's 0.07. And so the odds ratio is very simple. It's just your odds of exposure, which is your A, the formula is AD, so that's 2.3. And the odds of exposure for control, which is the BC, which is the second one, which is 0.07. So you divide 2.3 divided by 0.07, and you have 32.7 odds ratio. So now, based on what we know and how to interpret odds ratio, what does 32.7 means? An odds ratio of 32.7. So when we go back to how we interpret here, this is the Bible in interpreting odds ratio. When it's 1, the exposure is not associated with the disease. But when it's greater than 1, it means that the odds of exposure among cases is greater than the odds of exposure among control. So the odds of exposure among cases is greater. So that's how we interpret this, because we have more than one. We have an odds ratio that's greater than 1, that's 32.7. And therefore, our conclusion would be the odds of developing disease when the population is exposed to the raspberries is 32.7 times more probability of developing the disease was called cyclosporiasis. So that's what we call odds ratio. It's based on cases and case control studies. So now let's move on to relative risk. As I mentioned earlier, they have very different uses. So the odds ratio is very commonly used in case and control cases. But what about relative risk? Do we use this in a case and control? The answer is no. The relative risk, the measure of association for a cohort study. So as in the earlier slide, we define what is a case and control. A case and control can be a retrospective or prospective study, but a case and control is that you have assigned a group with cases and you have assigned a group of control that didn't have the disease. Whereas here, in relative risk, this is the measure of association for a cohort study. And in a cohort study, you actually, if you look back again for the definition of the cohort study, so right here, it's about exposure. Whereas case and control, there was already the disease. You see, that's a major difference. In cohort study, you start with exposure. Whereas in case control study, you already have the disease and you already have the group with no disease. So very, very different approach in the analysis of events. So in the relative risk, we are using cohort study. And cohort study is all about exposure first. We do not cohort the patient according to disease or no disease. We are control. In a cohort study, we start with exposure or non-exposure. So it tells us much more likely or less likely it is for people exposed to a factor to develop a disease compared to people not exposed to the factor. So the key word that I'd like you to associate with relative risk is always exposure. So I have mnemonics in my brain all the time, is that odds ratio, case, and control, disease and control. But RR has to be exposed or non-exposed. So once you have that, when you read a paper, you'll never be confused. Because when they say relative risk, you automatically say, oh, that means that they examined the individuals who have been exposed or not exposed. But then when you read the odds ratio, then you know that this is a cohort study that's like looking at, not a cohort, it's a study that look at case or what we call disease or control. And that's very typical in randomized controlled trial as well. If you want to know the effect of chemotherapy, well, you already will, you need to always have a control. So what do? One group will get the actual chemotherapy, and the other group will actually get a placebo. So, and that's how you know that whether the treatment is working or not. And that's why it's always reported as odds ratio. What the odds ratio, so when it is positive, that means that that the chemotherapy is working. So when they say that the odds ratio is about 10.5 times, so that means that the patient who received the actual chemo is 10 more times likely to achieve complete remission than the patient who received the placebo. So that's why we call it odds ratio. So when you look at the report that talks about odds ratio, always remember that the disease is already determined. It's there, and there is the control. So going back to the relative risk, it's about exposure. So the ratio of incidence rate in the exposed group and the incidence rate in the non-exposed group is what we call the relative risk. So this is the formula. You attach the rate, how many people were ill in group who were exposed, and then you use the attack rate. I see another, this is an early morning typo for me most of the time, but I can see it now that I'm awake. The attack rate is the incidence of a disease in a group and the number of people in the group who became ill divided by the total number of people in the group. So the attack rate is, first, you need to determine the number of ill people in the group and divided by the number of people in the group, the total number of people in the group. And then the relative risk is the attack rate for exposed persons divided by the attack rate for unexposed persons. See, there's two steps when we look at relative risk. We have to determine first the attack rate, and it's the incidence of a disease in a group. So, two steps. Attack rate first, and once we have the attack rate, then we can calculate the relative risk, because we need the attack rate for exposed persons and the attack rate for the unexposed persons. But it's very easy to determine the attack rate because you just need to know the number of ill people in the exposed and the number of people in the non-exposed, and that becomes your numerator and denominator respectively. So just like odds ratio, we have to have a Bible on how to interpret the results of relative risk. So when the relative risk is 1, it means that the risk of disease is similar in the exposed and the unexposed group, and that the exposure is not associated with the disease. My goodness, I'm seeing all my typos. And then when the relative risk is greater than 1, just very similar to odds ratio, but in a different context, because this is about exposure. When the relative risk is greater than 1, it means that the risk of disease is greater in the exposed than the unexposed group. And the exposure could be a risk factor for the disease. So, relative risk, you will see that relative risk is very commonly used in epidemiological studies about what is the relative risk for women who have been eating high-fat food compared to women who did not. So it's all about exposure to fatty foods? Or what is the relative risk of developing breast cancer among women who work night shift compared to those who did not? So the one that's exposed to the risk is exposure to the night shift, and those that are unexposed, those who did not do night shift. And what is, the attack rate? So you divide those. So the number of breast cancer in night shift, and then divided by the number of people who are working night shift. So if you're looking at a population of nurses, so the number of nurses who got the breast cancer while working as night shift, and the total number of nurses working in the night shift, that's the attack rate for that numerator. And then you will also need to calculate the attack rate for the non-exposed group. So the number of breast cancer in those women who work and those nurses who work night shift divided by, so the number of breast cancer for those women who did not work night shift, because we are now talking about the attack rate for the unexposed, divided by the total number of nurses who work night shift. And then you divide those attack rate of the exposed and the attack rate of the non-exposed, then you get your relative risk. So this is how we interpret it. Anything greater than 1 means the risk of disease is greater in the exposed than the unexposed group, and the exposure could be a risk factor for the disease. So this is how we build the science of epidemiology. This is how scientists and epidemiologists get to know that night shift actually really, really increases the risk for the development of breast cancer. We don't know the biological mechanism. Is it because of hormonal disruptions? Because when you don't sleep well, all of your systems are all wacko? We don't know. But epidemiological statistics, it's sort of like the tip of the iceberg. It's like, there's something wrong, but you can't pin it down yet. So that's what epidemiology is all about. Epidemiology is very good in outbreaks, because it immediately identifies that there's something going on, outbreaks in malaria. But then do we know the real reason, the cause and effect relationship of the factor? Not really. Epidemiology gives you probabilities. It doesn't give you exact science. So here in relative risk, if it's less than 1, it means that the risk of the disease is less in the exposed group, and that the unexposed group could be a protective factor. The lack of exposure could be a protective factor. So it has the same sort of train of thought as the same as the interpretation with the odds ratio, but this time the subtlety is about exposure for relative risk. So when you read an article on relative risk, always connect the dot that it is exposure. Whereas when you read reports or papers that talked about odds ratio, it talks about disease versus control or placebo. Treatment or placebo, disease or no disease, which is the control group. So here's the example of relative risk. The table shows a cohort of 3,000 smokers and 5,000 non-smokers to investigate the relation of smoking to the development of coronary heart disease over a 1 year period. Calculate the relative risk. So here, we have the 2x2 table. The one who smoke are called exposed. The one who do not smoke are non-exposed. So this is very different because in the odds ratio, it starts with the disease and then you have the control. Here you have this exposed and the non-exposed. And then on the column is the one who developed how many occurrences for the development of coronary heart disease among those who smoke and among those that do not smoke. And that's still the same. It's A divided by C. Whereas for the do not develop coronary heart disease, you have those that smoke would be B, and those that do not smoke among the called the non-exposed is represented by letter D. And the same total, you will always have 3,000 here. If the column is 84 plus 2,916, that's a total of 3,000. And if you have 87 plus 4,913, that's 5,000. So if you add 84 plus 87, that's 171. Take note of that number, 171. And then you add your 2,916 plus 4,913 equals 7,829. You add your 171 equals 8,000. So again, the 2x2 table always tells you that once you already have a predetermined total in the column, then the total in the row cannot be lesser or more than the total of the column. So rows and column total will always be exact. And that's the beauty of the 2x2 table, because it is a proportion. It's a marginal proportion that has specific limits and specific limitations based on the values of the numbers in the column or in the rows or vice versa. So for the incidence among exposure, which is basically A divided by C, it's 84 divided by 3,000. And then it will be 28.0. And then incidence among the non-exposure is 87 divided by 5,000, correct? So that would give you C divided by C plus D. So what's C? C is 87 divided by C plus D. That is your A divided by A plus B. 84 plus 296. 84 plus 2,916 equals, that's 3,000. So that's why 84 divided by 3,000 is 0.028, but it's 28.0 per 1,000. But you convert it by 1,000 times 1,000 equals 28. Okay? That's where we get the number 28, because we multiply it by 1,000, because our for the relative risk we're using per 1,000 as the unit. And then for the incidence among the non-exposure, which is your 87, which is your C, divided by the D, but then basically C plus D is 87 plus 4913. That's 5,000. So you get your 87 divided by 5,000 equals 0.174 times 1,000 equals 17.4. So the relative risk then is the incidence. We don't call it attack rate. The attack rate is, again, used in odds ratio, but here in relative risk, we're looking at incidence among exposure and incidence among non-exposure. And that's how we ended up with 28 divided by 17.4, and that you get a relative risk of 1.161. And so basically, when we look at this, we're going to report it to the newspaper, you know, news break. It will be in the spotlight that the exposure, here we're talking about men or women, because it doesn't say the gender. So basically, we would report this that men and women who smoke have a 1.61 higher relative risk of developing coronary heart disease over a 1-year period when compared to men and women who did not smoke. So that's 1.61. I don't think that people maybe will be scared with that number, but you could just say that the relative risk, it's 1.5, above 1.5 times more. You can't round it off to scare the people. You can't say it's 2 times. Your risk is 2 times. Always just stick to the number. When we do relative risk, we do not do round off. We always use the last 2 decimals. And we always stop in the last 2 decimals. So, any questions so far? These are the very fundamental concepts in epidemiology. You'll see this report every time we have typhoid outbreak in the Philippines, or cholera, or whenever we have an outbreak of, remember that the airline had the outbreak for, what was the type of respiratory disease? The ARS, I think, acute respiratory distress syndrome. And so for that, they have to really look at, what was the relative risk, because they have to determine exposure. And then once you have a treatment for ARDS, then you can already use the odds ratio, which means that you have the disease, which is the ARDS group, and then you have the control, which is group of patients who do not have, uh, who did not get the treatment for the ARDS, and then you find out whether what is the odds ratio of surviving from death due to ARDS if you receive a treatment. So again, once we start, when we don't know anything much about the disease, we always start with the relative risk. Once we already know the disease, then we can calculate the odds ratio. So I'm gonna skip these examples for you to just do at home. Now, the absolute risk is the risk of developing something over a specified time period. This is not very often talked about in the news. Absolute risk is about very specific to the probability of a certain disease will occur in a specified time period. So that's what you call absolute risk. So for example, what is the probability of developing lung cancer in individual who smoke for 20 years? So that's what you call absolute risk. You really put, exact number of years of exposure to the factors that can cause the disease. So you may have an example for 1 in 100 or even 1,000 chance of getting lung cancer, even if you have never smoked. So again, the key concept in absolute risk is that there is a specified time period. That's why we're able to calculate absolutely. So some discussion here about absolute risk. They can be expressed in different ways. You can say 1 in 10 risk of developing a certain disease in your life can be stated as a 10% risk or 0.1 risk, depending if you use percentages or decimals. If the risk of developing the disease was 4 in 100 in non-smoker, and the relative risk of the disease was increased by 50% in smoker, what is the absolute risk in developing the disease in smoker? Now here, the absolute risk is basically the risk that relates to the 4 in 100. And therefore, the absolute risk in developing disease increased to 6 in 100. So this is very confusing to the public, and I will tell you, absolute risk is not one of the most reported epidemiological statistics, because very few people can really grasp the concept of absolute risk. Plus they have to plug in that specific or specified amount of time. So basically, the same thing with prostate cancer. What is the absolute risk of dying from a low-grade prostate cancer in 30 years from the time they are diagnosed at the age of 50, or 30 years from the time they are diagnosed at the age of 65? Again, those factors need to be plugged in order to calculate absolute risk. And so there are so many variables that need to be plugged in, and this is not a very popular way of reporting epidemiology of disease. And the other one that's not very popular is the number needed to treat. This has gained a lot of attention, especially for mammography. So the number needed to treat is the number of people who need to be involved in a treatment for one person to benefit. So you can just imagine. So basically, this is more of a cost-benefit analysis. It literally tells you, in order for us to appreciate the benefit, X number of people needs to have the treatment first. So it has a very specific context for the interpretation of the statistics, which is called the number needed to treat. So here, what we have given here an example is if a drug company reported that drug X reduced the relative risk of developing certain disease by 25%, and if the absolute risk of developing the disease was 4 in 100, then this 25% reduction in relative risk would reduce the absolute risk to 3 in 100. Another way to view this is that if 100 people do not take the drug, then 4 will get the disease. However, if 100 people do take the drug, then only 3 people will get the disease. You could just imagine what's the difference. You will need 100 people to take the drug in order to have 3 people will get the disease. Now, that's what you call the number needed to treat. So sometimes, government officials might say, maybe we should not treat because we needed X amount of patients to be treated in order to even appreciate what the benefits of the treatment is all about. And that's very common now in localized prostate cancer patients. There's a lot of arguments that, for localized prostate cancer, some patients will even die with not from the localized prostate cancer. They will die from heart attack. They will die from other diseases or other medical condition because it's such a slow growing type of cancer that some patients are 80 years old are not even diagnosed with prostate cancer unless they do the PSA. And so PSA is actually has a lot of debate about what is the number needed to treat, or what is the number needed in order to appreciate the value of PSA, which will lead to early detection of prostate cancer. The same thing with mammography. That's why the guidelines for mammography and the guidelines for PSA testing are always changing based on the latest statistics, because they have to really base their recommendation on the number needed to treat. So here's an example of the Lipitor, which I will let you read because we're running out of time. And prevalence and incidence, this is very common, especially if we go to communicable diseases. We always report this. We want to know the prevalence and we want to know the incidence and what's the definition. This is always part of the board exam in the Philippine National Board Exam. I will always remember this. Incidence is always new. Prevalence are what's already there. So that's the way how my brain works. And so when I take the exam, I never get the wrong answer because I always just have very specific term that I connect to the key concept. So that's probably one of my strategy in test taking, is that a concept is always attached to a word to me, and I will never sway my decision making. Once I have attached it to that word, that's it. I look for that word and then I'm definite with my answer. So prevalence means the number of people who currently have the disease, whereas the incidence is new. Consider diabetes can have a very low incidence, but with high prevalence, because there are very low number of new cases, but there are many, many people because they don't die right away. So there are many, many people with diabetes. So they have high prevalence. Whereas a common cold can have a very high incidence, especially when it's flu season, and have low prevalence because the common cold is almost just part of an acute condition. They're not 24/7, they're not year-long, and they're not chronic. So that's a very good example of the application of the concept of incidence and prevalence. The problem with prevalence is that it only has the number who currently have the disease, and the estimates of prevalence are not necessarily comparable. There are very different methods of collecting the data. And there are conditions such as cancer that go into remission. So that's very problematic, actually, in cancer. When you say, what is the prevalence of breast cancer? Well, the one who gets into remission, are you going to count those people? That still remains debatable. And nobody really tackled that question. They still include the one in remission as prevalence. What about incidence data? Well, there's also a problem with that because you're only accounting for new cases and not the ongoing treatment. The actual number of people affected by a condition can be less than the incidence tells, such as a single individual may have multiple cases, such like the common cold. So you always need to look at incidence and prevalence data with caution, basically, because it has its own limitation. Incidence, again, can be affected by factors, can be affected by events in a year, and therefore incidence can change from year to year. Just like what's the incidence of cholera in after the typhoon, where we don't have toilets and we don't have safe water, then the incidence is very high. But then you should interpret that incidence data with caution because you know that something induced the higher incidence. So that's just the way how, epidemiologists always report their epidemiological data, is to always, when it comes to incidence and prevalence, always interpret it with caution and always remember that they can be affected by the events or conditions or calamities or extreme situations. So we need to always remember that we need to compare apples with apples and orange with orange. So try to always remember that when your sources are unclear, when your methods of accumulating data are different, and when your categories and your criteria for the disease classification is different, then you should not do what we call a meta-analysis. You should not do systematic reviews because there are specific guidelines in doing those things, because when you do systematic reviews and when you do a meta-analysis, you are supposed to compare apples with apples, and you're supposed to compare orange with orange. And therefore, when you look at the data sources, you always need to know, okay, this study, they utilize this type of instrument to measure anxiety and stress. And then this study, they utilize the Hamilton depression scale. While this study, they utilize the PHQ, Public Health Questionnaire number 9. So when you look at data, when they do not have the same way of measuring the phenomenon of interest, and when they don't have the same context, especially if it's a depression among hospitalized patients versus depression in the outpatient clinic. So different location, different setting, you cannot combine those studies. You cannot make a conclusion. And the first step for us to really understand the disease is to develop disease classification, to develop disease categories. And that's why the World Health Organization will always have guidelines on classifications of B-cell disorders, the guidelines for classifications for T-cells lymphoma, because without those unifying guidelines, you cannot compare You cannot have a true accounting. You cannot have a true epidemiology of the disease. It's very important. So, especially in my specialty with cancer, the World Health Organization is definitely the leading organization, healthcare organization that's spearheading criterias for uniform standards all over the world. So if you have, for example, the World Health Organizations, they have developed the whole classification for osteoporosis. So what is considered as severe, what is considered as moderate, what is considered as mild, and what is considered as osteopenia. And those are based on standard deviation score of the DEXA scan, dual energy absorptiometry x-rays. And so with those unifying guidelines, we will be able to truly measure the incidence of osteoporosis in the world. So that's what epidemiology is about, is always remember that when you are thinking of epidemiology, you can think of epidemiological report, is it locally? Is it globally? And when you say globally, are the methods, are the sources, are the categories, are the context, the age grouping, reporting bias, all are taken into account before you would say, this is the global incidence of such and such disease. So I will leave that with that, and we'll have it's already 9 o'clock my time. So we have now almost used 2 hours. And I think the next slides are just talking about 2 more. I will not discuss the controversy of mammography, but I will discuss this the screening for disease detection, which is validity and sensitivity, and then that's the end of our 2-hour session. Because the chi-squared test statistics and test of independence using chi-squared statistics is available already online. I recorded it last year, so you could just view them according to your own schedule. So for the screening for disease detection, so validity is very important. This is a very important concept when it comes to rigor, or what we call quality. Validity of the test is defined as the ability of a test to distinguish between who has the disease and who does not. So validity is really important. In psychological measurements, validity refers to the ability of the instrument to measure what it intends to measure. So here in the context of detection of or screening for disease, validity is exactly the same in terms of the core concept of the ability of the test to distinguish between who has the disease and who does not. So does it really detect the one with the disease? And does it really distinguish the one who do not have the disease? So that's in the psychometric measurements, validity is defined as the ability of the instrument to measure what it intends to measure. So the very, very important concept in epidemiology is validity. It has 2 components, sensitivity and specificity. So the sensitivity of the test is defined as the ability of the test to identify correctly those who have the disease. So sensitive, always identifying those who have the disease. It's always positive for those who have the disease. So, for example, in your HIV testing, why do we have Western blot as a confirmation? Why do you think we need to do Western blot? We already do HIV test antibody testing, right? But when it is positive, we always do a Western blot for confirmation. What do you think is the relationship or the rationale for that in relation to the topic of validity? Anybody wants to raise their hand? It's okay, just try.
For me, Doc, I think it is if it is a confirmatory test, it would probably ensure make the results more accurate when it comes to the cell count of the HIV patient.
Okay, any other? Try to frame your answer based on sensitivity.
For when you talk about sensitivity, it is when the exam or the test is, what do you call this? How the patient or how the patient's cells react to the test itself. How sensitive are the cells to the test? Is that it?
So when we have Western blot as confirmatory, it tells us that perhaps it's not 100% sensitive. It tells us that perhaps a certain percentage of patients who tested to have the disease actually did not have the disease, right? And that's because these biomarkers could be present in other conditions. It's not exclusive to HIV. So the presence of HIV antibody could not be 100% all the time reflective that they have the disease, and that's why we do. But it's very small. It's the accuracy, the sensitivity of the HIV antibody is very high. What about specificity? It is defined as the ability of the test to identify correctly those who do not have the disease. So, a very good example for this is always the HIV antibody test. What is the sensitivity and what is the specificity of the HIV antibody? Can anybody Google that? Quickly. Let's Google sensitivity and specificity of HIV antibody. There are many publications of that. Sensitivity and specificity of HIV antibody tests. You see, the sensitivity of HIV tests is approximately 99 to 100%. As for the specificity, only one false positive result per 50,000 to 100,000 tests is expected. Because of that, we have to do a Western blot, just because it's not 100%. You see, every time you don't have a 100%, you need to do Western blot, because that will compensate for the weakness of the test. You only have 1% chance that it is not HIV, but you can't take the 1% chance, because that's still not 100%. And that's why you have to do a Western blot. And for the HIV rapid test kits, the sensitivity for the blood is 95%. Specificity is 99.9, and that's why there's always Western blot. So here's an example of, again, the 2x2 table. And that is, your column on the left is those that test positive and those that test negative. And we call it the D plus are true positive, and the D minus are the false positive. For the one who tested negative and are called, and are false negative, we call them also the D plus. And then under the those who test negative but had true negative, we call them the D negative. And to calculate the sensitivity, you have the formula, which is TP, the true positive, divided by true positive plus false negative. So that's your D plus. Basically, true positive plus the false negative are the D plus. And then for specificity, you have your true negative divided by the true negative plus the false positive, and that's your D minus. So D plus is represented by sensitivity. D minus is represented by specificity. And then when it comes to looking at the negative predictive value, then you will need to get the TN, which is your true negative, divided by the true negative plus the false negative. And in order to get the positive predictive value, you will use the formula, the true positive divided by the true positive plus the false positive. So these are, again, what we call the the theory of marginal probability. When your value in the column totals to the value the total value in the column must be equal to the total value in the row. And that's how we are able to really determine sensitivity and specificity, because if you are not sensitive, then it reflects to your specificity. If you are not specific, then your number for sensitivity also gets affected. So that's what you call the 2x2 table. Is so important in epidemiological investigation because of what we call the theory of marginal probability. which basically says whatever is the total in your column when the values in the rows are already predetermined, then the total also of the rows has to be equal to the total of the column. So exactly mathematics. So if you have a sensitivity of 87, then that will be reflected that your specificity will also balance it out to make sure that the total will be 100% predictive value. So sensitivity is true positive divided by true positive plus false negative. It answers the question, how many people test positive who really have the disease? How sensitive is this test in picking up people with disease? Just because it says I don't have the disease, could it be wrong? A lot of false negative. Always remember that. Sensitivity will always answer those questions. What about specificity? These are the true negative. It answers the question, does the test correctly classify those without the disease as negative? If I take this test and it says I have the disease, could it be wrong? A lot of false positive. So specificity is false positive. It addresses false positivity, whereas sensitivity, it addresses false negative. And that's it for epidemiological statistics.
Thank you, Doc.
All right, well, very good. I will send the slide set and I will also send you the link to review the chi-square statistics at your own time, okay?
Thank you, Doc.
And I have a quick question. On next week, is it possible that we do it on a Sunday? Because I'm flying to Europe at 4 p.m. on Sunday, my time. So I can do our fourth week, Sunday, 8 o'clock time, same time, but instead of Monday, we'll do it on Sunday for the fourth week. Is that okay?
I'm fine with it, Doc.
I'm okay, Doc.
Sunday's okay. Perfect. Anyway, if you can't make it, we will also do a recording so that for those who will miss the class, they can always view this in YouTube. I will post it on YouTube. All right,
Okay,
take
Doc.
care.
Thank you, Doc.
Thank you so much. All right,
Care.
Bye,
bye-bye.
Doc.
Bye.